Hi everyone, welcome to CEE122 recitation 2. And in this recitation, we'll go over the problem in homework 2. So let's straightforwardly start with the first problem, 2.47. So in this problem, we basically want to solve the surface tension for different sides of the diameter. So according to the problem, we want to calculate the surface tension of the water for different tube size in 1/2 inch, 1/8 inch, and 1/16 inch. So I will denote those diameter into D1 is equal to 1/2 inch, D2 is equal to 1/8 inch, and D3 is 1/16 inch. Okay, so to calculate the water column, the height changing water surface due to this surface tension effects, we will apply the surface tension force equation. So the equations look like this. The delta H, the difference in height that caused by the surface tension, is equal to 4 sigma divided by gamma d. Okay, and the surface tension according to the table in the appendix, the table 8.5 in the appendix, we note that the surface tension for water is approximately 5 times 10 to the power of -3 pound per feet. So this sigma is equal to 0.005 in this case. Right. And the specific weight for water, this gamma, is 62.4 pound per cubic feet. Okay, so after we have this equation, we can just plug in all the values into here. So the delta H for D1 is equal to 4 times 0.005 divided by 62.4 times this D, we will apply D1. This is 0. Because we want to use the units in feet, so 1/2 inch is 1/24 feet, and I just change all the value first. This is equal to 1/96 feet. This is 1/192 feet. Okay, so we just plug in D1 here. Is 1/24. So we will know that the delta H is equal to 0.00769 feet, and that is equal to 0.0923 inch. Okay, so we can use the same equation with different D value to calculate delta H D2 and I will not write the equation again. I will jump into the answer directly because you just need to change this d into this d2 here. So the answer will be 0.0308 feet is equal to 0.369 inch. And for the d3, the delta H for d3 is equal to 0.0615 feet, which is equal to 0.739 inch. So as you can observe here, as the diameter of this tube getting smaller, the height brought out by the surface tension will be higher. Okay, so that is for the problem 1. Let's move to the next problem. So in this problem 3.6, as shown in this figure, a mouse can use the mechanical advantage provided by the hydraulic machine to lift out an elephant, and the problem asks us to derive the algebraic equation that gives the mechanical advantage of the hydraulic machine shown below here. Okay, and we assume that there's the piston are frictionless and massless. Okay, and after that, we want to determine a value of d1 and d2 so that the mouse can support the weight of the elephant. Okay, so for the subproblem A, the definition of mechanical advantage is equal to weight lifted by mouse over the weight of the mouse. Okay, so we denote that into W2 over W1. So if we plug that into this figure, here have the weights 1, and here have the weights 2. Okay, so that's the definition for the mechanical advantage. Then next, we want to derive the equation. So the weight of the mouse, this weight 1, is equal to the pressure at this point times the area of this piston. So the area for a circle is pi r squared is equal to pi 2 over 4 d over 2 to the square. So this is the area. So we will times this up, which this will be pi d square d1 square divided by 4. Yes. Okay. And weight 2 will have the similar equations, the pressure at this point, and because they are in the same height, so the pressure are actually equal to each other, so we will denote into just P for that common pressure times the area of this piston, pi d2 to the square divided by 4. Okay, and because we know that the pressure are actually the same, so we want to represent the equation into P. Let me write here. P is equal to, you move this term to the other side. So that will be W1 full W1 divided by pi D1 square. For this part, P is equal to 4W2 divided by pi D square 2. Pi D2 square, sorry. Okay, so P is equal to P, so we have the equation D1 square equal to 4W2 pi D2 square, and you cancel out the common term. So we reorganize this equation bit, move this W to the bottom part here, move this D1 to the upper part of here, right hand side. So we will get that W1 over W2 is equal to D1 square over D2 square. Okay, so this is the mechanical so we actually have want to calculate W2 over W1, so we just switch the side. W2 equal to D1 square. Okay, so this is equal to this. So this is fits to our definition of the mechanical advantage what we have defined here. Okay, so this is the equation for that. And for the second sub-problem, we want to give a value of D1 and D2, and because we already know the mass for the mouse is equal to 25 G, which is 0.025 kg, and the elephant, the mass of the elephant is equal to 7,500 kg. So we actually know the W2 and W1 already, and the weight is equal to mg, so the W2 over W1 is equal to, the W2 is the elephant, so the mass is 7,500 times g, and W1 is for mouse, the weight of the mouse is 0.025 times g. So this will give out the value 300,000, so 300,000. And we know so this will equal to D2 divided by D1 square. Okay, so let's assume that if D1 is equal to 0.07 meter. Then we can use this equation to calculate the D2. Okay, so D2 in this case, let me still write the equation down for you. Is equal to D2 0.07 square. So with one unknown, you can solve this D2 is equal to 38.3. Okay. So we can conclude that with this mechanical advantage equation that we just derived, we know any D1, D2 that satisfy the ratio of D2 over D1, D1 equal to square 3,100 will satisfy this condition. Okay, so here we gave the example that if D1 equal to 0.07 meter, then we will need D2 to be 38.3 meter in this case. Okay. Now let's go to the next problem. So problem 3.16, for a closed tank with the Bowden tube and gauges tapped into it, what is the specific gravity of the oil and the pressure reading on gauge C? So we want to solve the specific gravity for oil. Specific gravity for oil is equal to the specific weight of the oil divided by the specific weight of the water. Okay, this is the first things that we want to solve, and the second things is the pressure reader on this C, so which is we want to solve this PC. Okay, and the constant that we know from the table 8.5 is that the specific weight for water, this gamma water, which I will just write gamma instead, to be 9810 Newton per cubic meter. Okay, so to solve this, we will use the concept of hydrostatic equation. So what is hydrostatic equation? Here is it. So basically, you find a 2 point so the hydrostatic equation is P. So that's find a point at this baseline here. So you can read the pressure at this point by this gauge, which is 58.5 kappa. But you can also calculate the pressure at this point using the material on top of it. So the hydrostatic equation we can list it for this question is that PA plus gamma ZA is equal to PB, the pressure at B point, plus gamma ZB. Okay, so we already know that the pressure at for the first part is equal to 550,000 Pa. Okay, because we already know PA here, plus the gamma ZA, because we want to calculate the pressure at this point, so you need to calculate the gamma ZA at here. And this specific weight, we will need to use the OU's specific weight. Okay, and ZA is equal to 1 meter here, 1 meter. So times 1 is equal to PB, which is the pressure at this gauge, that is 58,500 Pa. Plus, and because it's already on the bottom of this dash line, so we have this OU but the height is 0, so we can just cancel out this term. So by solving this equation, we will learn that the specific weight for the OU is equal to divided by 550,000, which is equal to 8,500. Okay, and to calculate the specific gravity, which we have defined above, is equal to water, right? So this is 8,500 divided by the water is 9,810. So this gave us 0.87, and this is our specific gravity for oil. So basically, you just need one hydrostatic equation to calculate the pressure, to use different component to calculate the points at this bottom on this dash line. Okay, and we can use a similar idea to calculate the pressure at the C point. So we will list out that this is for the subquestion 2. PC will equal to P at the bottom of oil plus gamma times 1. So the pressure, we want to calculate the pressure at this point, so we can calculate is equal to the pressure on the bottom of the oil at this point plus the specific weight of water times the height here, which is 1 meter. And the bottom of the oil is the pressure at this height here, which is 58,500 500 plus the pressure contributes by at least 0.5 meter distance, 0.5 times, and the material here is oil, so you will times the specific, actually not the specific gravity, the specific weight of oil, and plus the specific weight of water times 1. And we plug in the value. We already know that the gamma oil is 8,500, so just plug all those values in. Times plus no 9810. Then you will get 72,560 Newton per meter square or part. Okay, so we have solved for the subproblem 1. And subproblem 2 using the hydrostatic equation. Now we're going to move on to the next problem. So this problem is given that we have 390 Newton force to apply to this F1 with the 4 centimeter diameter, which is 0.04 meter, and we want to calculate what is the magnitude of the force F2 that can be resisted by the piston with the 10 centimeter diameter, which is 0.01 meter. Okay, and we will neglect the weight of the piston. So again, we will apply the hydrostatic equation. So you draw a line here, because they are same material, so these parts will be cancelled out. So the part from here will equal to the part on the right hand side. So we will write the hydrostatic equations. P1 plus gamma Z1 will equal to P2 plus gamma Z2, and P1, the pressure in general is the force over area. Okay, so P1 is 390 Newton divided by the area, which is pi 0.04 square. This is the area for this circular piston, plus gamma, and the gamma here, because this is oil and it's already given the specific gravity, so the gamma oil, the specific weight of the oil is equal to the specific gravity 0.85 times the specific weight of water. In this case, the gamma water is equal to 9810 Newton per cubic meter. So 9810. Okay, so we can write that down. 0.85 times 9810 times Z1. And because we cut a line at here, so Z1 will be 0. And it will equal to P2, which is the F2 that we want to solve, divided by the area of this piston tube, pi 0. Sorry, I was wrong here. This is 0.1. Okay, 0.1 divided by 2 to become the radius and square. That's the area for this piston tube. Plus gamma, which is the same, 0.85 times 9810 times Z2. 2 meter. Okay, so we have the equation that with only one unknown, which is F2. So after you solve this equation, you should be able to get that F2 is equal to 2310 Newton. And the pi here is equal to 33.14. Okay. Oh, you can just type the pi using your calculator. Right. So let's move to the next one. So we have a similar problem, and we want to calculate the pressure at the center of the pipe B. So again, we will use the hydrostatic concept, and because for the pressure, we only consider the vertical distance. So we first convert the right-hand side of the figure into the vertical distance. And we can draw a line here. And because we have the ratio for 3, 4, and these parts will be 5. So this will be 40 centimeter. This will be 30 centimeter. And this is equal to 0.3 meter. This is equal to 0.1 meter. This is for 0.5 meter. Okay, so as I said, as previous problem, we will cut off the surface here. So the parts on the right hand side, the hydrostatic on the right hand side will equal to, on the left hand side will equal to the right hand side. Okay, so that's mean PB plus gamma times C1 will equal to, and because these parts on the same material, so we can cancel it out, We just care about this, the parts above this surface, equal to, and this part is 0.1 meter, so this remaining part is 0.2 meter. Okay, we'll equal to PA, that's denoted here as A, plus gamma A, it's gamma A, gamma B, times Z2. Okay, so PP is what we want to solve. Gamma B is already given by the problem, that is 10,000 par times Z1, which is okay, this is confusing. Let me write ZB and ZA instead. Okay, so this is ZB, this is ZA, times ZB is 0.5, will equal to PA, and because it's open to the surface, so the PA is equal to 0, and plus 0.2, gamma A is 20 kappa times ZA 0.2. So PP will equal to 4,000 minus 5,000. And that is minus 1,000 par. So it's also equal to minus 1 kappa. Okay, so again, this problem is the hydrostatic problem. You can use this equation here to solve the only unknown variable in this problem, which is this pressure B. Okay, so let's go on. Okay, so for this problem 3.43, we will still use the hydrostatic concept, but with slightly more complicated problem. Okay, so let's start. The problem asks us to solve the pressure at the center of the pipe A, which is here, and I will denote it as PA. And we have another open open tube at the left-hand side of the tube here, and we denote this as PB, and PB is equal to 0 because it's open to the open air, right? Okay, so let's think. The pressure at this point A is provided by the weight of the liquid above it, but because the tube will then turn, so the liquid at this part is actually provide a negative force to this point A, and when the tube turn again, the liquid at the left tube also provide a positive force to this point A. Okay, so with that concept in mind, we can write down that these parts provide a positive force to this PA at point A, and this part provide a negative force and this part provide a positive force again. So we can before listing out the equation for the point for this PA, we can just do another trick. We can draw a line here, and because the liquid here and liquid here are actually the same, they are both oil, and they provide the equal weight, equal force but with the different directions. So these parts will just cancel each other out. And similarly for this turn, we can cancel the force provided by these two parts because they are the same liquid and they but they are in different directions, so we can cancel them out. So we just need to consider these remaining 3 segments liquid in this pipe. So we can start to list out the equation that PA is equal to the force provided by the liquid above it. So it is gamma water times the height of these parts, which is given by the problem already, that is 150 centimeter, and that is 1.5 meter. And we indent move to the middle tube, it provides a negative force, so it actually minus gamma, and now it's oil. The liquid in the middle tube is oil, so gamma oil times the length, which is 150 plus 30 centimeter. So it's 180 centimeter, that is 1.8 meter. Okay, then we down to turn again, it's become a positive sign, and now we have a 90 centimeter of water, so it's gamma water times 90 centimeter, that's 0.9 meter, plus the mercury part, that is 60, 30 plus 30, 60 centimeters, that is 0.6 meter, so it's gamma oil times 0.6 meter, and plus the pressure provided by this tube, that's PV. But we already know that's PV is 0, so we can just cancel it out. Okay, so now we have this hydrostatic equation for the PA. Then we want to calculate the specific weight for water, oil, and the mercury. Oh, okay, so this part is actually wrong. It's not oil, it's mercury. Okay. So for the water part, for the specific weight for water at 10 degrees Celsius is 9810 Newton per cubic meter. It's given by the table 8.5, yeah. And for the specific weight for oil and mercury, you can either use this table A4 here, or we can calculate directly using the specific gravity that given by the problem. And because in this table, they actually is not at 10 degrees Celsius, so this is just for reference. You can still find the specific weight for different material online with the similar table shown in this table A4. But because the problem already gave us a specific gravity for each of the material, so we can use that to calculate the specific weight, which is equal to the specific gravity times the specific weight of water. So for oil, the specific gravity is 0.8 times gamma water, that's 19810, and for mercury is 13.6 times 9810. Okay, and then we can use a calculator to find out the corresponding value. And for oil is 7848, and for mercury is 133416. Okay, now we have these three values. We can just plug it back to this equation. So we will get that PA is equal to 9810 times 1.5 plus 0.9. Why is that? Because we have two terms that's related to the water, this term and this term. So we just take this out and plus these two together and become this term. Okay. Then move to the second term. Minus oil is 7848 times 1.8. Then the last term, mercury, 133416 times 0.6. Okay. Then again, we will utilize our calculator. Then we'll get the value that is equal to 89467.2 par. So it's roughly equal to 89.5 copper. Okay. So this is the end for the recitation. And I will see you in an in-person recitation.